Hello, everyone. I hope everyone is doing well and safe given these times. Today, we'll be talking about a paper that has been having a really controversial discussion, which is are we really making much progress, which is a worrying analysis of neural network recommendation approaches, discussing deep learning approaches in recommender systems, how effective they are, and the reproducibility of the papers. Today we have the main author of the paper, Maurizio, who is a PhD student in Polytechnical University, and he has been working in the recommender engine field for a couple of years now. So welcome, Maurizio, and it's really good to have you.
Thank you. Thank you for inviting me, and thank you to all of you who are listening now.
My pleasure. So yeah, it's your field right now.
Okay, so in this presentation, I'm going to present the results of a couple of our recent articles. In addition to the one that Omar mentioned before, there is an extended version which is currently available on arXiv. So if you're interested, you can have a look. And all the materials are available as well. So if you want to replicate our experiments, check our conclusions, you can do that independently. So a bit of context. We all know that in several fields of our scientific publications, there is what is referred to as a reproducibility crisis, which means that it is difficult to be able to independently verify and reproduce results published by other authors. Now, as I'm sure you can agree, the independent reproducibility of published research is a cornerstone of the scientific process. Referring more specifically to computer science, there has been a series of articles trying to assess the level of reproducibility for machine learning and artificial intelligence research. The results, however, turned out to be rather poor, observing reproducible articles in a quota of between 20 and 60%, trying to assess the level of reference and the field. This is only one of the problems we encounter. There is another. Several years ago, Armstrong, in one of his articles, observed that there was, at that time, no evidence that ad hoc information retrieval technology had improved during the past decade or more. That is a rather strong statement. But it was from 10 years ago. How about now? Last year, in 2019, Yang observed that we do not find evidence of an upward trend in effectiveness. The best reported results are from a decade ago, and no recent neural approach comes close, which is rather surprising considering the number of articles that have been published in the last decade, especially now that new complex and neural methods are all the rage. How is it possible? Well, a possible direction comes from an article written by Lin, again in 2019. He says, it is not difficult to find neural ranking papers that demonstrate winning by showing statistically significant improvements over weak or inadequately tuned baselines. So we have, on one side, a problem in terms of reproducibility, which tends to be low, and on the other side, a problem in terms of how challenging is the evaluation that is reported and used in those studies. What we want to do in this what we did in our articles is to try to assess the level of reproducibility and the progress that was made in the recommender system fields in the last years. A couple of preliminaries about recommender systems. Now, a recommender system is basically an information filtering system whose purpose is to assist the user in the exploration of the vast number of options that many online and web services have at their disposal. You can find recommender systems everywhere, from e-commerce, on-demand multimedia, music recommendation, movie recommendation, social networks, friend recommendation, hashtag recommendation, news recommendations, and so on. In their most simple version, a recommender system suggests the users, provides the user with a list of options which the user might find relevant. And depending on the scenario and on the information you have at your disposal, several types of techniques can be applied. So the first part of this study is a reproducibility study. So the first thing we want to do is to define what is reproducibility for our purposes, and how do we select the articles we want to analyze. The criteria we use for the selection of what we call relevant papers are as follows. We selected a certain number of conferences: SIGIR, KDD, the Web Conference, EGCAI, Wisdom, and Rexis. All of them are typical venues for recommender system research. This is not an exhaustive list, but still, you may find others. We selected articles, long papers published between 2015 and 2018, those years included, and restricted them to papers applying neural technologies to the traditional top K recommendation task, which means you compute the recommendations based on the past user interactions. We did not include articles using deep learning to perform, for example, feature extraction from multimedia data, or things like group recommendations and such. Also, we only considered articles evaluating their proposed model on at least one accuracy or ranking metric. So we did not include articles only focused on rating prediction, because the industry and research community has been moving away from rating prediction for a while in favor of item ranking. Now, reproducibility. The definition of reproducibility, there are different definitions you can find in different studies. For the purposes of this, the definition we adopted is the following. The numerical findings that are reported in the study we analyze should be closely reproducible by using the original artifacts. I stress two things. Closely reproducible. We are not looking for exact reproducibility, but at least we would like to be able to confirm the findings in the paper. Also, we use the original data and source code as provided by the authors. A couple of more specific information. We require the source code to be able to execute without extensive intervention. So the source code should be runnable, at most with minimal modifications from our side. We did not include articles providing, for example, a skeleton implementation of the model, or articles with missing parts or dependencies we could not resolve. Then, to the data. There are two cases here. The preferred scenario is when we have access to the original train test split as provided by the authors. If not, we should have at least available a public dataset. So the evaluation of the article should include at least one publicly available dataset, and the information in the paper should allow us to reproduce the preprocessing and splitting as done in the article. A specific case is we do not include articles using datasets that have been crawled from websites, because we can't guarantee the data has remained the same. As you can imagine, we had a few issues in trying to reproduce the results. In all cases, we sent an email to the authors, all the authors of the paper, asking for assistance, and we waited a maximum of 30 days for a reply. If we were able to receive a reply and address the issue, the paper is considered reproducible. If not, it is not reproducible. Now, to some statistics. In this table, you will see the reproducibility ratio of the various conferences, that is the number of relevant papers which we could reproduce. As you can see, there are two conferences, KDD and EGCAI, with rather high reproducibility ratio, above 70%. Which is high, yes, but still means that 1 in 3 to 1 in 4 articles are not reproducible. Bear in mind that these are rather small numbers, so it's not a reliable statistics. Dub has a 50% reproducibility ratio, Sigayar 30%, and at the almost bottom of the list is Rexis, with out of 7 relevant articles, only 1 reproducible. Wisdom has a 0, but we only found 1 relevant article, so it's a bit of an outlier, perhaps. Overall, we could identify 26 relevant articles, but we could only reproduce 12 of them, which is 46%. This number is in line with other studies, but it's still a bit low, less than 50%. Here, I'm just briefly going to mention the various articles we have found, only to highlight that the technologies they rely upon are quite different. For example, MCREG uses metapaths on a graph. Then there is a variational autoencoder. The neural collaborative filtering algorithm is perhaps the most cited and used neural recommender system you can find. Uses latent factor models, again a variational autoencoder. Spectral collaborative filtering uses the spectral domain of a graph. We have a convolutional model. We have, again, latent factor models. So you see, under the umbrella term of deep learning, a lot of technologies are applied. Now, the first part of our study is a reproducibility study, but the second one is an evaluation study. So how did we run our own evaluation? Very important to mention is that we applied the same identical experimental procedure as in the original paper. So we used the same data, the same preprocessing, the same train test split, the same metrics and cutoffs as reported in the original paper. As per the hyperparameters of the models we report, there are 2 cases. In case of the deep learning algorithm, so the proposed algorithm we analyze, we use the original hyperparameters. This, and it is important to stress this, is appropriate only because we are relying on exactly the same evaluation protocol as the original paper, datasets included. For the baselines, of course, we don't have hyperparameters, so we use a Bayesian search exploring 50 cases. The set of hyperparameters and ranges, as well as distribution, is available in the online material of the paper. There are quite a lot. We use Bayesian search instead of the more common grid search because it is a much more effective strategy in our experience. Briefly, I'm going to describe what are the various baselines we report, just so that you can have an idea, even if you're not specialized in this topic. The first one is a non-personalized algorithm, which means that it provides to all users the same recommendations, and it recommends the most popular items, the one that received the most interactions. Then there are 2 nearest neighbor algorithms, item KNN and user KNN. They are simple algorithms developed more or less 20 years ago. They leverage the item-item or user-user similarities between other items or users computed via heuristics. The main idea is the many interactions they have in common, the higher is the similarity. But there are a number of heuristics: design similarity, Pearson correlation, the Jacquard index, Tversky dice, and so on. We use a few. The second group is graph-based models, P3 alpha and P3 beta. They are a bit more recent, and they are based on a transition probability in a graph, which is composed by item and user nodes. The 2 are connected if there is an interaction between them. And the higher the transition probability between a user and an item, the higher the probability it will be recommended. Lastly, a few simple machine learning baselines. The first 2 are based on an item-item similarity as well, but in this case, the item similarity is learned. In case of SLIM, the first one via a linear regression. In case of ISR, using a linear shallow autoencoder. ISR is a very recent model. The nice thing is that it allows a closed form solution, so it is possible to compute the similarity directly without gradient descent. It is incredibly fast. Then there are 2 matrix factorization algorithms, which are based on the decomposition of interaction data as the product of 2 low dimensionality matrices. So they project the interaction data into a latent space. The second one, pure SVD, uses the traditional SVD decomposition, so it's a very well-known mathematical operation. Now, to our results. I'm going to provide an example of one algorithm and then a summary of the various results we had, because there are many. Oh, yes, some numbers to give you an idea. In order to write the study, we had to evaluate 900 models, so model datasets, which required more than 41,000 evaluations due to the hyperparameter tuning phase and more than 250 days of Amazon AWS. So it required a lot of time. Anyway, so here is an example of the results for one algorithm. The columns report the accuracy or ranking metrics, and the numbers you see at 5, at 10 represent the number of recommendations that were provided to a user. Now, as you can see, the bottom line, which is the deep learning algorithm, is never in bold, which means that at least 2, in one case 3, otherwise 4 simple baselines are able to outperform that deep learning algorithm in this case. This is a scenario we found very frequently in our experiments. Another case which is particularly interesting is this. It's still CMN and on another dataset. Now, as you can see, we have CMN outperforming personalized baselines, in this case, by a lot, by more than 10% in some cases. However, if we add a non-personalized baseline, the results change completely. The simple topopular model is able to outperform everything, every personalized baseline, by a huge margin. How is this possible? Well, in this dataset and on this experimental procedure, the data is so unbalanced towards highly popular items that it is not really possible to effectively personalize the recommendations. The topopular was not present as a baseline in the original article. Now, let's summarize what we found. In this table, we're going to see the various deep learning algorithms we analyze. Here are just a few of them, and I'll explain why in a moment. And the numbers represent how often those deep learning algorithms were competitive against simple baselines. Now, if we consider only the k-nearest neighbor and graph-based baselines among the simplest we have, we see that 3 algorithms are never competitive. The others are to some extent, but in between 30% and 50% of cases, which is really not much. However, if we add the simple non-personalized recommendation, we lose an algorithm, as I showed you before. The particularly surprising, in a negative sense, finding is when we add the simple, mostly linear matrix machine learning algorithm. None of those 7 is able to outperform the baselines. As per the others, they are competitive to some machine learning baselines to a limited extent, in between 8% and 37%, less than 40% of measurements. In those cases, this mostly means that either they are competitive only in a specific dataset, or they are in a few measurements scattered around the experiments. There is only one algorithm which showed to be able to consistently either outperform or at least be at par with the various baselines, which is multiply and is a variational autoencoder. Now, these results are, well, not very good. Let's discuss them a bit. First, we observed that the reproducibility is rather low. Only 46% of the algorithms could be reproduced. Now, why? I can mention 2 aspects. The artifacts were not available, or we contact the authors, but we couldn't address our question. As per the artifacts, which means source code and data, in one case we had the source code, but not the data due to copyright issues. The remarkable bit was that in 4 cases we had the source code, but the source code was not working. Sometimes we encountered missing dependencies. Sometimes we encountered errors in the code itself, which means that no one tested the code before providing it online. In other cases, there was no documentation to the extent that we were not able to build the code. It was C++, I think. In the majority of cases, 8, the artifacts were not available. We contacted the authors. In some cases, it was not possible to share the code due to non-disclosure agreements. In other cases, the code was lost. In others, again, we received no reply. As I said, among the disappointing to an extent findings of our analysis is that contacting the authors often proved unhelpful. In 3 cases, we received a reply and we were able to solve the issue we had. We thank again the authors for their kindness. In 9 cases, we did receive a reply, but we couldn't solve the issue. For example, we couldn't define an experimental procedure to be able to obtain the same results the author had. And in 12 cases, we received no reply, which means that in almost 90% of cases, we could not address our requests contacting the authors. Then we found a series of methodological problems in the articles we analyzed. Some of them are related to the article, others are related to the source code provided by the authors. The first one is that the experimental design is very different across articles and to some extent seems arbitrary. Why? Well, one of the problems we see is that all articles, or almost all articles, claim to improve the state of the art in a very general sense. But then, in what looks like a contradiction, at least in our point of view, from our point of view, the evaluation is only done in very specific conditions. Furthermore, articles which seem to be written to target the same scenario are then evaluated in different ways, which makes the comparison opaque or impossible. A common trend we noticed is that there is no explanation on why that specific experimental design was chosen. And the result is this. This is a list of all the articles we analyzed, and we report the data sets they were evaluated upon and the trained test plate that was adopted. Now, you will not be able to find 3 of them which are evaluated in the same conditions. Most of them are evaluated in unique conditions, so it is impossible to compare all of them. And here I'm not even showing the various metrics that are used, accuracy and ranking metrics, there are several, and the recommendation list length that is considered. Another issue we observed is a tendency to select and propagate weak baselines. Now, what do I mean? We observed the disappearance of simple k-nearest neighbor and graph-based baselines, as well as simple machine learning baselines, in favor of more complex neural approaches and recent neural approaches. However, there is a widespread tendency to use default hyperparameters taken from the original article. However, as I showed you before, most of articles are evaluated in different conditions, which means that it is often possible to find the baselines as reported in the evaluation procedure to be suboptimal. So the evaluation reported in those articles is not really challenging. Here I want to stress a very important point, that when you run an experimental evaluation, all algorithms must be optimized for the specific scenario, the specific data set, the specific evaluation procedure. Otherwise, your comparison is meaningless because you are taking algorithms that were evaluated, that were optimized by different articles in different scenarios, and you are taking those hyperparameters. You have an inconsistently optimized set of baselines. Again, the comparison using those results is meaningless. An interesting phenomena we observed, as I mentioned earlier, is the propagation of weak baselines. Now, what do I mean with this? The scenario is the following. A new complex model is published. However, the evaluation is poor. This model appears to be outperforming baselines, and then it becomes a state-of-the-art. Then, later algorithms, later papers use it as an example of state-of-the-art baseline. Here is a graph which shows all the algorithms we analyze, and the two algorithms are connected if the later algorithm uses the previous one as baseline. Now, you can see that all algorithms in 2018 use at least one of the previous algorithms as example of state-of-the-art baselines. However, we could observe that none of the algorithms from 2015 to 2017 is indeed a strong baseline, which means that over time, the evaluation becomes less challenging. Lastly, another surprising finding is that by looking at the original source code as provided by the authors, we could find a number of errors in the evaluation procedure. In 5 cases, the provided data split was inconsistent with the description, either because we could find items or users which shouldn't have been there according to the preprocessing phase described in the article, or in one remarkable case, the test data had a completely different distribution from the trained data, and there was no reason for this. In 6 cases, 6 out of 12, so it's 50%, we could see that the number of trained epochs was selected using the test data, optimizing recommendation accuracy on the test data, therefore causing information leakage. In 3 further cases, the criteria was not described and a fixed number of epochs was added in the paper, was written in the code. So it means that in 9 out of 12 algorithms, the criteria to stop the training of the model was not transparent, or it was plain incorrect. In 2 cases, this is even more remarkable, the best metric value was not selected according to a certain epoch, but rather it was reported as the maximum accuracy achieved by the model throughout a long training phase. So you could observe that different metrics refer to different epochs, and the results are therefore inconsistent. In further 3 cases, we found errors in the metric computation such that the values couldn't be reproduced because they were not correct. Now, a question I'm getting asked a lot, is this a problem of deep learning? Short answer, no. Longer answer is that, as I showed you before, problems in reproducibility and methodological issues in the evaluation have been reported far before deep learning algorithms went widespread, since Armstrong in 2009. So the problem is actually much wider. Okay, so how can we move forward? Now here I'm going to try to provide a few suggestions, a few ideas on how we can try to move forward and address these problems. So one important point is that we should try to remember that the results of a paper must be reproducible for several years. So using a public repository and providing as much information as possible, especially details perhaps of the training or the preprocessing which you could not fit in the paper due to space reasons. Also, try to ensure that the environment is reproducible, for example, using virtualization. Now, machine learning and deep learning libraries get updated very often, so it can become very difficult after a couple of years to reconstruct a consistent environment if the dependencies are not being described with high precision. Also, do not assume that the authors or that your students, if you have PhD students, will reply to every question they received from other researchers. Regarding the methodology, a particularly important point, we believe, is to try to find a way to justify the evaluation procedure. Now, what is the scenario your algorithm is targeting? Why is that data set, that splitting, that metric, that recommendation list length representing a meaningful scenario? Also, important is to try to improve the reliability of the experimental protocol, adding simple baselines, and improve the focus we have during the review process on the evaluation of the paper. As a side note, I could also say that we perhaps are too dependent on the concept of outperforming some selected baseline on some experimental conditions. There are many things which could be relevant in a real case scenario that we might want to evaluate. Our algorithm may have several strengths, particularly quick train time, improve the diversity in certain relevant conditions, or maybe particularly resilient to the changing of the data over time that in any real case scenario a company experiences. Now, we are pursuing this research direction, so if you are interested and you want to have a look, please follow our lab and or drop us an email if you want to collaborate for these activities. Thank you for your attention. Now, if you have questions, I'm here.
Thank you, Maurizio. It was really, really interesting, and I enjoyed it a lot. We have a couple of questions, actually. So the first one is, when you send the author's email, what were the responses if they don't address the question? What do they respond with?
Well, as I said, in the majority of cases, we received no reply. Now, in some cases, we were able to engage in a constructive conversation, while in others, we simply received replies like, we cannot provide the information at this point, or we are working on an extended version, and so we cannot reply. Now, in some cases, in one case, as I said, the source code and data was lost. I suppose someone was not saving the materials properly, or perhaps a PhD student graduated and took the data away. So we encountered a lot of these unfortunate problems.
Okay. The second question is there any specific reason why you selected from 2015 to 2018 papers, or was it random?
Well, since the beginning of this work was at the end of 2018, it took more or less a year. So we started from the latest publications we had, and then we moved backwards until we could find basically no other articles. As you see, we could find no relevant articles in 2016. We added 2015 because one of the algorithms was cited in later research. Now, it's a never-ending work, because based on the number of conferences and the articles that are published, by the end, as soon as you have an evaluation complete, you have other 50 articles published.
Okay. Another question is, do you think this is happening, like these kind of research is coming out that is not reproducible because conferences are only looking for state of art, beating state of art, or is it because authors are assuming that whatever has been done before them is correct and they just want to beat it? They don't check the correctness of the previous work. What do you think the problem is?
Well, it's a bit of both, perhaps. The underlying assumption is that if a paper is published, then I can trust their results, I can trust their findings, which is not always the case, unfortunately. Then we should remember that the reviewers that are reviewing papers are the same people who may write those papers in the same subjects, perhaps. So it goes a bit of both ways. In conferences like KDD, who are enforcing, they have, if I recall correctly, reproducibility criteria in the review form. We can see that the reproducibility is rather high. In conferences that don't, the reproducibility is a bit low. So perhaps this is a product of two effects. The conferences are not paying enough attention on it, but also the researchers are not.
Okay.
So, by the way, I'm a very young researcher, so I am not here to tell anyone how they should do their job. I'm just here to provide elements for discussion.
Well, it's a really nice discussion so far. Thank you for that. I don't see any other question, but I have a couple of ones. So the first one is, would it be okay if you can share with us the architecture of the two models you're talking about, which is the neural matrix factorization and the variational autoencoders?
Yes. Okay, so just to give you an idea of what happens. This, again, as I said before, is, I think, one of the most cited algorithms applying neural recommendations. You have at the bottom the input data, which are users and items. It is a one-hot encoded vector. Then you have two fully connected layers. You see that there is one called MF, which is matrix factorization, item vector and user vector, and the other is MLP. It's a multi-layer perceptron, item and user vector. Why? Well, because the model is a hybrid of two components. One is, as you can see at the top left, in the top left of this architecture graph, a simple element-wise product, which is the traditional dot product we use in most matrix factorization algorithms. And on the right, there is a neural component, which is a multi-layer perceptron, which takes the two embeddings and aggregates them with a neural, in a nonlinear way. The two are then concatenated in the uppermost layer, which is called the new MF layer, and then again the score is computed. This model, I think, is one of the most popular because it is also extremely flexible. The embeddings can have different sizes, and you can replace or alter the inner structure according to the information you have and the type of scenario you want to model. As per the autoencoder, variational autoencoder, I'm taking this very simple image from the original article. The idea is really that you take the user profile, which is a Boolean vector. The items the user interacted with are didn't interact with are zeros. The items the user interacted with are ones, or a different value if you have explicit ratings, like between 1 to 5. And what you want to do is you want to be able to reconstruct the user profile using an autoencoder. Now, the general idea is just that simple. However, several strategies can be put in place. For example, a problem which is sometimes overlooked is how sparse the data in a recommender system is. Consider an e-commerce website. You may have a million articles in the catalog, but how many of them could you possibly buy in a reasonable amount of time? Dozens, maybe 100 or so. So the greatest majority of the data is zeros. There are several strategies that can be put in place to avoid your model being overwhelmed by zeros. And some of the best performing autoencoders use tricks like this. Again, the models are rather simple, as you can see. Okay. I can mention if another type of architecture, which is the convolutional one, if you want.
Yes, please.
Okay. Cool. A couple of algorithms use this type of structure. The bottom part is very similar to NewMF in that you have the one-hot encoded item and user vector. Then you have a fully connected layer with the embeddings. You compute an outer product of them, so you have a square, which is an interaction map, and then a convolution is applied on it. The idea is that it should be able to model more effectively the nonlinear dependencies between the embeddings. Although we couldn't find any of those techniques was able to outperform the baselines, so whether it is a sound approach is still not entirely clear.
Mm-hmm. Okay. The other question is basically how would you increase the reproducibility, do you think? What should be done to increase reproducibility in these conferences?
Well, the main problem we encountered is that the materials were not publicly available, so something that may encourage the authors in put this extra effort, because of course providing the materials is extra effort, is to include in the review process something which asks the reviewers whether the materials have been made public. Now, of course, there is an underlying problem, which means if you want to be able to assess the real reproducibility, you have to execute the code and the experiments, but we cannot ask reviewers to try to do the work we did because it takes a lot of time. The minimum requirement, I think, could be to ask the reviewers to check whether there is source code and available materials. The rest should be down to the community. If increased awareness of this problem starts to spread, perhaps other studies like ours will be made, and there will be a little more pressure on the authors to be careful on how they do their experiments.
That definitely makes sense. What is the goal of your research? We have a question about that.
Sorry, could you please repeat?
What is the goal of your research?
Well, the goal of my research was simply to take a snapshot at recently published research on a neural recommender system in a very specific scenario. Again, I'm considering a very specific scenario of recommender system research, and have an idea on how easy it is to reproduce those results, and whether those algorithms were really competitive. In part, this is due to the fact that in past research we had trouble reproducing results of algorithms which were considered in the state of the art, and we're wondering, are we perhaps doing something wrong, or there is something else going on? So it comes from a personal experience.
Okay. Since my research is also a recommender system, but I want to ask you that question. What kind of recommender engines, or what kind of deep learning do you think is actually safe to use, or it showed good results in the recommender engine?
Well, this is really dependent on what you want to do and on the type of data you have. What I could observe is that very frequently simple algorithms like the item-based KNN, so the nearest neighbor algorithms, or the graph-based algorithms, were able to achieve very high recommendation quality with very, very little computation time. So I would suggest you start from those if you want to try new solutions, but consider that depending on the type of information you have, those may not be flexible enough, for example, or those may not be suitable for that specific data set you are working on. But the suggestion I would put forward is to start simple rather than try immediately to target a very complex model, because they are difficult to train, they are difficult to optimize, and they are difficult to they struggle a bit with the type of well-structured data we have in recommender systems.
Okay. Another question, since I don't find any yet, is if you have something like, I don't know, group recommendation, session-based recommendation, all these kind of recommender engines that simple algorithms don't really work well with it. What would, like, for example, for session-based recommendation, NLP techniques have been proving really, really good results, even in reproducibility, right? When you're talking about even graph-based recommendation, graph neural network has been doing well so far. Do you see like deep learning being more active in these kind of recommender problems, or still try the simple recommendation before you do it?
Well, as a general suggestion, trying something simpler is always better than starting with something complex. Surely, if you are targeting scenarios where you have more complex behavior or complex signals, session-based recommendation is an example. Sequence-aware recommenders, you have a certain type of behavior. In those cases, the using simple KNN algorithms may be not really effective, although some examples of algorithms able to compete, at least with the current state of the art in terms of sequential recommendations, have been proposed. I think important concept is that there is no universal solution which is able to address all of your problems, and that sometimes the difference of the underlying behavior you have in different data sets or the type of data split you make is sufficient to change the relative performance of different models.
Okay, so I have a question that showed up twice, and my personal experience is not good with it. Is what is data what about the data visualization in the recommender engine?
What do you mean?
Data visualization, right? So when you're having, like, for example, you're talking about NLP, you have really nice word graph, you have a lot of visualization in the recommender engine, but in NLP, but how can you visualize your model, and how can you visualize your data in recommender engines?
Well, this is a bit outside my area of expertise,
Hmm.
so I'm not really sure if I can provide you with an
Yeah.
exhaustive reply to this question. I'm sorry.
So from my experience, it's really hard to do data visualization for a recommender engine, and the reason is if you're gonna go with visualization, you're already looking at what the data is right now. And the thing with the recommender engine is you're always trying to find the pattern that is not really dependent on the visualization right now. I don't know. I didn't have a good experience with visualization recommender systems. Um, Another question I think is graph neuron. Since you recommend using simple model to start with, how can you determine when more complex ones are needed?
Well, the um, easier way to determine whether a more complex model is needed is to have a simple baselines and try a more complex model. But as a general rule, if you have very simple signals alone, for example, past user interactions, um, it tends to be rather difficult, in our experience at least, to leverage the modeling capacity of neural approaches. If you have more complex signals, like different types of interactions,
Hmm.
I'm talking about, for example, in movie recommendation, you have a recommendation, then you click on the description of the movie, you watch the trailer, you read the plot. Those kind of different behaviors begin to create a heterogeneous set of signals. And the more heterogeneous is the set of signals you have, the easier it is that a neural nonlinear recommender is able to leverage it. Remember that those deep learning algorithms began with complex problems like image recognition, computer vision, and such. So otherwise, we are just using them on a table of data.
True. You're 100% right. Another question: when you were trying to produce the result, were you able to do the explainability part? Because explainable AI is a huge thing right now.
It is. However, in I think none of the articles which we analyzed, explainability was considered as an important problem. So most of those simply perhaps to a certain degree, treat the recommendation problem as a simple classification problem,
Mm.
but do not take this explainability part into account, which, as we know, is very important from the
Mm.
user side. But again, I am not a specialist in terms of explainability, so I'm not sure if I can provide you with a complete answer on this topic.
Okay.
Similarly,
Um,
if I may just add something, a few questions I received highlight one thing that I said, and I'm going to repeat it. Is there are many things that are extremely important when you build a recommender system, and we sometimes tend to forget that in the end there is a person using that. So, if we only report recommendation accuracy, we are forgetting an important part of the problem. Besides, a few studies have pointed out, user studies, that users tend not to perceive or not to notice very small accuracy gains. So, to some degree, this push towards higher accuracy is not necessarily going to translate in better user satisfaction. And several other aspects of the behavior of our models could be interesting to take into account.
I
Should be
fully
taken.
agree with that. Yes. I'll go a bit technical back to your presentation, and you were talking about training and testing split, right?
Mhm.
Each study had their own test split, train split, and they might have not reported it in the paper. So, do you have any insights on that splitting?
Well, I saw a number of different types of splitting, picking a certain quota of interactions from the train to build the test data, selecting just one train interaction per user, um, taking a fixed number of interactions for all users and using everything else in the test data, ranking the positive item, so the test item, against a fixed number of negative items, 1,000, 999, 150. Um, in the end, the type of split that you make can create several different scenarios because it alters the way in which your test data represents the train distribution. So do not consider as equivalent and interchangeable, those different evaluation procedures, because they can have an impact on the way your algorithm behaves. To have an idea of how what this impact is, perhaps it should be, perhaps you could try to add, for example, distributional diversity metrics to have an idea of how your recommendations are distributed across the items. Perhaps user-wise diversity to have an idea of how biased towards popular or unpopular item your algorithm is. So there are a series of things you should do. It is very difficult to provide an answer which fits all the problems because the variety of scenarios is huge.
Okay.
I hope I am to some degree answering.
Yeah, it's easy to split the way you think your model is going to do better. Doesn't mean it is.
Besides, if your model is going to do better in a specific scenario and not in another, that is not a negative side, this is a positive side, because you are able to clearly identify the scenario of successful applicability of your model. Perhaps if your model works very well on popular items, you have a specific scenario, a niche you can target, and in which you can beat everything else. So trying to find when you are the most competitive is an asset, but you shouldn't try to claim that you work better everywhere because it is impossible.
True. I think we can have this as a last question is how an architect of the recommender system knows the user do benefit from this improvement, right? So even if the accuracy gets slower, maybe the user is going to benefit more. But I think that could be tested straight up by doing live A/B testing, right? So if you wanna see if the user is actually benefiting or not, and you don't want to rely on the metrics, then you do A/B testing, live A/B testing.
The great problem is that if you want to have an idea of the user perception, you have to do an A/B testing, you have to perform online studies, which are complex, slow, expensive. So I can understand that there is a bit of difficulty from the the author's side to be able to really evaluate how is the user perceiving a model, which sometimes, the perception of the user might change according not only to the accuracy of the model, but also according to the incorrect recommendations. What type of those recommendations are? Maybe they can improve the novelty of the recommender, of the serendipity of the recommender, engaging the user and exploring more widely. So several things are not really that visible if you run only offline studies.
Sure, 100% agree. I think that will be it. I'm not gonna ask the last question. Okay, that will be it. Thanks a lot, Maurizio. It was really, really interesting. And we hope we have you again in future events. Thank you.
I do too. Thank you.
Thanks a lot. So Jiang can stop the presentation. Okay. I need to.